Oxidation numbers are useful in redox chemistry because they are a number that tells you the amount of electrons lost or gained during the oxidation or reduction process. A positive oxidation number tells you that an atom or an ion has lost electrons. For example, if you have aluminum 3+, that means aluminum has lost 3 electrons. If you have Na+, that means a sodium atom has lost 1 electron. A negative oxidation number tells you that an atom or an ion has gained electrons. For example, if you have O2-, that means oxygen has gained 2 electrons. If you have something like PO4 3-, that means PO4 has gained 3 electrons to become the phosphate ion. So there are some rules for assigning oxidation numbers that we have to follow. They're listed right here. I'm going to give you examples of each rule, so it's better just to go through the examples than to sit here and read through each one individually. The first rule is that pure elements have an oxidation state of 0. Any substance that is in its elemental form will have an oxidation number of 0. So this includes like Hofbrinkels and other unique substances like listed here, sulfur S8 and phosphorus P4. Those are elemental forms of those substances, so they would have an oxidation number of 0 if you came across them in a chemical reaction. The second oxidation number rule is the oxygen rule. Oxygen will always have an oxidation number of -2 except when it's in peroxide. And the only peroxide that we're ever going to deal with in honors chemistry is hydrogen peroxide. So the only time oxygen will be -1 instead of -2 is in the molecule H2O2. So in all of these molecules here that have oxygen in them, every single one of them, oxygen is -2 until you get to this last one where you see H2O2, that is hydrogen peroxide. That is your only exception for oxygen. In that case, oxygen would have a -1 oxidation number. The third rule is the hydrogen rule. Hydrogen will always have a +1 oxidation number. The only exception here is if it is a metal hydride, because metals will always have a positive oxidation number. They always lose electrons. Most of the hydrogens you see in these examples here are going to have an oxidation state of +1. The only exception is right here, lithium hydride. Lithium is a metal bonded to hydrogen. If it's just a metal bonded to hydrogen, in that example, the metal will have the positive oxidation number and hydrogen will be a -1. H2O2, that's an exception for oxygen, but not for hydrogen. Hydrogen would still be a +1. The fourth rule is the ion rule. So any monoatomic ion, the oxidation number is the same as the charge on the ion. Easy enough. So sodium would be a +1 oxidation state. Oxygen, O2- would be a -2 oxidation state. Calcium 2+ would be a +2 oxidation state. And I think you can get the gist of it from there. Tin would be 4+, aluminum would be 3+ for the oxidation state. When you have a polyatomic ion, the oxidation states of the atoms have to add up to the overall charge on the ion. So the oxidation state of nitrogen and oxygen in this example must add up to a -1. So check this out. This is how you do it. Oxygen is always a -2. So then you have to get the oxidation numbers to add up to a -1. Well, if you have 3 oxygens in NO3-, each with an oxidation state of -2, that means you have a total of -6 from the oxygen. So then you just have a little bit of algebra. What plus a -6 is going to give you -1? That's how you're going to determine the oxidation state of nitrogen. Well, in this case, it'd be +5. So nitrogen, in this case, would have a +5 oxidation state. So how about NH4+? Well, you know hydrogen, following the hydrogen rule, is always a +1. So then you have to add up the oxidation numbers to get an overall +1 charge. Well, you have 4 hydrogens, so that means you have a +4 from the hydrogens. So what does nitrogen need to be in this case in order for the overall charge to be a +1? Well, it has to be a -3. So in this case, nitrogen has a -3 oxidation state. So you can see right there, there's an example of nitrogen with +5 oxidation state and nitrogen with +3 oxidation state. So different atoms can have different oxidation states, except for those ones we have specific rules for, like hydrogen and oxygen. How about sulfite ion? Has to add up to a 2-. You know oxygen is a -2. If you have 3 oxygens, that would be a -6. So the only way to get a -2 charge overall is to have sulfur have an oxidation state of +4. Okay, I want you to pause the video and try these last 2 examples out on your own. When you think you got it, press play and check your work. The last oxidation number rule is the summation rule. So when you have a neutral compound, the sum of the oxidation numbers has to add up to 0. So it's much like the ion rule for polyatomic ions, but it applies to compounds here. So if you have a 2-element compound, you can just look up the common ions by finding out what column the atom is in the periodic table. If you have a 3-element compound, do the outside 2 elements first and then the middle one, because the middle one will have the variable oxidation state. So if we have H2O, we have 2 rules for those. Those 2 rules cover that. So hydrogen is a +1, oxygen's a -2. You can see this would add up to 0 because we'd have a -2 from the oxygen, and we have 2 hydrogens, each with a +1 charge. So we have a +2 total charge from hydrogen, so it adds up to 0. Another 2-element substance, so sodium is in group 1 of the periodic table. Everything in group 1 has a +1 charge on their ions, therefore a +1 oxidation state. Chlorine is in group 7 of the periodic table. All atoms in group 7 of the periodic table have a -1 charge on their ions, so chlorine has a -1 oxidation state. When you do manganese chloride, manganese is a transition metal, so you want to do chloride first. It is in group 7, so it has a -1 oxidation state. We have to get a neutral charge overall. So if we have 2 chlorines with a -1 oxidation state, we have a -2 from the chlorines, which means manganese must be a +2 and its oxidation state +2. When you do 3 or even 4-element compounds, do the outside elements first and then the inside. So that works pretty nicely on this first one because we know hydrogen is a +1 and oxygen is a -2. So the whole thing has to add up to 0. We have a -6 from the oxygen since we have 3 oxygens. So we have a +1 from the hydrogen. So we just have to do a little algebra and figure that out. Nitrogen in this case must be a +5. Nitrogen in the nitrate ion will always be a +5. When we look at NaClO3, we know oxygen's a -2, and we know sodium is in the first column of the periodic table, so it will have a +1 oxidation state. This has to add up to 0. So we have a -6 from the oxygen, since there's 3 of those, +1 from the sodium, and then in this case, chlorine is also going to be a +5 oxidation state. How about potassium permanganate? Once again, we know oxygen's a -2. We know potassium is in group 1 of the periodic table, so it would have a +1 charge on its ion, so a +1 oxidation state. This has to add up to 0. 4 oxygens would give a total charge of -8. The potassium is a +1, so then to make the overall substance neutral, manganese must have a +7 oxidation state. I'm going to partially help you with this next one that has 4 elements, and then I want you to pause the video and try out the last 3 examples on your own. In this next one, we know oxygen has a -2 oxidation state, hydrogen has a +1 oxidation state, and sodium is in group 1 of the periodic table, so it also has a +1 oxidation state. So knowing that, you should be able to figure out phosphorus. Use the same method of attack to figure out the nitrogens in NH4NO3. So pause the video and try those out. When you think you got it, press play and see how you did.